Okay, Physics 11H, here we are. A little lecture on impulse. There's some pretty good notes on it right here. Impulse is a concept that we use to introduce momentum, which is mass times velocity, which we'll derive in a second here. But the Regents really likes to talk about impulse in terms of force times time. So I'm going to quick go through basically what's already written on the packet here that you'll be doing for homework, and then I'll do a little example for you. I'm going to try to keep this fairly short. So when we give something a push, right, just like on the packet here, you give it a push or a pull, apply a force to it, right? That causes the object to change its motion, right? If it starts from rest, V initial equals 0, it'll gain a velocity, right? If we start to apply a net force to it, an unbalanced, let's say this is frictionless here. Vf equals something big and positive. Now, we say that the force, one way you can say this, provides an impulse. All right? Provides an impulse, which is a change in momentum, which we'll talk about in a second here. Try to fix this glare a little bit, moved it down a little bit. I'm going to have to just see if I can move this light, but it's a bit of a competing thing here where I need the light, but I don't want the reflection. So I might have to just get a little creative with it, see if I start to move it, the picture gets dimmer. Anyhow, so when we apply force to something, a net force to something, we give it an impulse, we change its momentum. So how do we define impulse? Well, it all starts with F net equals ma. And we plug in the definition of acceleration, F net equals m delta v over t. All right? And then we just rearrange this equation, multiply both sides by t, and then we rewrite it a little bit, write it up here. We say F net times time equals m delta v. This side of the equation we call change in momentum, and this we call impulse. The amount of force times the length of time it's applied for gives us a change in momentum, mass times change in velocity. I'm going to put a link to a Bill Nye video that talks about momentum. It's kind of interesting. It's a entertaining video, but a few of the scenes are questionable, which I'm gonna try to make a little fun task, watch it and figure out which scene is the most inappropriate without graphically describing it. But anyhow, you'll see what I mean when you watch the video, trust me. F net times t equals m delta v, mass times change in velocity. And we define this as change in momentum. All right, F times t, impulse. So let's just quick talk about this part right here a little bit more. All right, impulse we said was this. All right, now here's something super annoying. They give impulse the symbol J, which looks like joules, right? It's a terrible idea, but they do it. Nobody really uses the term impulse, right? Or the symbol J. You call it change in momentum. If you do call it change in momentum, you pretty much just call it this. This is change in momentum. And the symbol for momentum is P, a lowercase p, right? And if it's change in momentum, it's delta P, which it's change in momentum because it's m delta v. The momentum at any given time would be just mass times the velocity at a particular time, which we'll get to in a second. So you can have, you don't have to always have a change in momentum. You can determine an object's momentum when it's moving with some velocity just by multiplying its mass times its velocity. Now, let's look at, so J equals F net times T. Sometimes it's average force, sometimes it's net force, sometimes it's just a single force, and you're figuring out the impulse due to it, and this is M delta V. The units here are newtons times seconds or kilograms times meters per second. I'll leave the proof to you to figure out if these two are the same or not, right? A newton is a kilogram times a meter per second squared. You cancel out one of the seconds and you end up with the same unit as this. So when we multiply force times time, we call it impulse. When we multiply mass and change of velocity, we call it change of momentum. But they are the same thing. They're the same thing. An impulse, it's kind of like work and energy. Work causes a change in kinetic energy. You can determine the work by doing force times distance. You can determine the change in kinetic energy by doing 1/2 mv squared final minus 1/2 mv squared initial, right? Change in kinetic energy. Here, we can figure out the impulse given to an object by a force by doing force times time. We can figure out the change in momentum that results by doing mass times change of velocity. Usually what we're doing is, I tell you the force and the time, you figure out how much that particular object would change its velocity. Or we measure the change in velocity of a particular object and figure out what force must have been applied, right? So that's typically what we do there. And I'll do a little example here, similar to the packet, all right? So we'll talk a little bit more about instantaneous momentum, all right? This idea that if an object's moving, all right, moving along with some velocity, has some mass, we say it has a momentum of its mass times its velocity. In fact, in upper level physics, when we talk about electrons and protons moving through space, we don't really reference their velocity by themselves. We pretty much always reference their momentum that they're carrying, because that tells us a lot about the object, its momentum. If you look at Newton's second law, F net equals ma, and we say F net equals m times delta v over t. Well, look, m delta v, that's change of momentum, delta p over t. And in fact, in upper level physics courses, this is how you write Newton's second law. It's the rate of change of momentum. It's change of momentum over time. We don't even write ma half the time. We usually just write F net equals delta p over t. You don't need that for the region. It's just an interesting sidebar. So let's look at an example here. All right, let's say let's say we give an impulse. We give an impulse of positive, and it is a vector quantity. I should have mentioned that. Vector quantity, because it is directed with the force, and we'll see that in a second. We give an impulse of positive 100 newton seconds to a 15 kilogram object, initially at rest, let's say. Determine its final velocity. All right. Haven't left myself much room here, but whatever. So impulse equals change in momentum, or change in momentum equals impulse. Sometimes we're given the force and time, sometimes we're just given the impulse. J equals delta P, so plus 100. I'm really messing up today. Didn't drink enough coffee, perhaps. Plus 100 newton seconds equals mass, 15 kilograms, times the change in velocity. We're looking for the change of velocity, so divide both sides by 15. 100 by 15. Oh, is like, I don't know, 6 or something. 6.7. All right, so our change of velocity, I ran out of space here, but I'll write it up over here. Our change in velocity is positive 6.7 meters per second, right? So if our change of velocity is positive 6.7 meters per second, that must mean our final velocity is positive 6.7 meters per second because the initial was 0, right? So if we started off at rest and we gained positive 6.7 meters per second, then our final must be positive 6.7 meters per second. So that's a basic example of being given an impulse, figure out the final velocity of the object, right? So usually though, that's something the regents will do. What we'll often do is we'll say, okay, a force of 10 newtons, let's say negative 10 newtons, is applied to an object, to a, let's say, 100 kilogram object for I got to give you initial velocity, an object initially moving at positive, let's say, 35 meters per second for 3 seconds. Determine the VF of the object. All right, so a force of negative 10 newtons is applied to a 100 kilogram object initially moving at positive 35 meters per second for 3 seconds. So the force is applied for 3 seconds. Determine the final velocity of the object. So let's write down some stuff over here. M equals 100 kilograms. V initial is positive 35 meters per second. The time the force is applied is 3.0 seconds. The force itself is negative 10 newtons. And we're going to look for the final velocity. All right, so I have all the important stuff written down over there, almost out of screen. I apologize for that. Let me draw a picture to try to figure out what's going on here. So initial velocity, boom, 100 kilograms. That's pretty darn big. Initial velocity is positive 35 meters per second. The force is negative, so our force, we're gonna pull against it. I'm gonna draw the force vector a little bit different than our velocity vector to kind of be able to show what's going on here. So we have a negative 10 Newton force. So this object should slow down. We'll see if it actually turns around if the final velocity comes out being negative. But let's go ahead here. F net times time equals m delta v. See, what I like to do is I like to solve this problem for delta v and then figure out what the final velocity is. Some people like to just immediately put in v final minus v initial for delta v, but what I find when people do that is they miss a sign here and make a mistake. So let's just solve for delta v. So F net, it's going to be negative 10 newtons being applied for 3.0 seconds to a 100 kilogram object, and we're going to find the change in velocity. So divide both sides by 100. All right, so 10 times 3 is 30 over 100 is about 0.3, 0.3, and it's a negative. Now, what are the units? Well, you're going to have to trust me on this, but it does come out to be meters per second, and Newton is a kilogram times meter per second squared times a second divided by a kilogram. So kilograms cancel, seconds, meters per second equals delta V. So check it out. This thing barely lost any velocity from this weakling force. It's a big mass. 100 kilograms is a big mass. 10 newtons is not much of a force, right? So by picking a big mass, we see that's difficult. Now, if the mass was smaller, let's say it was 10 kilograms, right? This would be 30 over 10. This would be 3. We change our velocity by quite a bit more. So VF in this case, since delta V is negative 0.3, VF must be our initial velocity, plus 35 meters per second, minus 0.3 meters per second. We're taking away that velocity. If the force was positive, we'd be gaining that velocity. All right, 34.7 meters per second, which to 2 sig figs is 35 anyway. So what do we really accomplish there? All right. Anyhow, a couple little quick examples. I'd like to see if you could do number 1 and 2 for homework. we'll talk a little bit. I'll make another video a little bit more about the stuff on the back there, 5 and 6. That is important. Haven't assigned those yet. We'll figure it out. All right, have a good one, guys. Talk to you later.